Hello, my name is Ngoc Nguyen. Today I will be presenting the joint work with Cody Gonzalez, which is the paper titled Effects of Decision Complexity in Goal-Seeking Gridworld, a comparison of instance-based learning and reinforcement learning agents. This is a pre-recorded presentation for the 2020 International Conference on Cognitive Modeling. Decisions under uncertainty are often made by weighing the expected costs and benefits of the available options. The trade-offs of costs and benefits can make decisions easy or difficult. For example, some decisions are easy when we choose between option of low cost and high value and the one with high cost and low value. Conversely, other decisions are complex. That's when we choose between a low cost, low value and high cost, high value options. This decision's complexity even increases given uncertainty in the cost and values. As an example of making decisions under uncertainty, we consider the goal-seeking task in Gridworld that analyze a broad range of applications such as search and rescue missions. Basically, in the task, an agent or a player must navigate an environment with uncertainty about its surroundings. That means the agent doesn't know where obstacles and the goal are. The objective is that within a time limit, the agent must achieve a goal, usually the highest value object. To help us understand how decision trade-offs might work under different levels of decision complexity, we use two models in our research. First, reinforcement learning models are commonly used for tasks that involve learning from interaction, and it has been prevalent in addressing the goal-seeking task in Gridworld. But recently, the concern has been raised that the development of reinforcement learning is mostly centered on how to solve computational problems efficiently, rather than replicating in detail how humans learn. Alternatively, cognitive modeling is focused on understanding and explaining human behavior by representing the cognitive steps by which a task is performed. In particular, instance-based learning theory was developed to cognitively account for how humans make decisions from experience through interactions with dynamic environments. However, so far, it still remains unclear how reinforcement learning and instance-based learning models perform the Gridworld task under different levels of decision complexity. Therefore, in this work, we evaluate how a cognitive model based on instance-based learning theory and two well-known reinforcement learning algorithms learn to make choices in a goal-seeking Gridworld task under uncertainty and increasing degrees of decision complexity. We consider the Gridworld environment that is made up of a 11 by 11 grid as illustrated in this figure. The number of obstacles varies from 1 to 5, and they are put randomly in the grid. There are 4 targets of different values, which are represented by 4 color objects: blue, green, orange, and purple. They are also put at random locations. There is one agent starting at the random location, and it makes sequential decisions about which actions to take up, down, left, or right to obtain the highest value object, which is the ring object in this example, within a 31-step limit. A sequence of decisions that the agent made from initial location to the end location creates a trajectory represented by a dotted red line. In the task, an episode ends when the agent decides to consume or reach any of the 4 objects, or by reaching the 31-step limit without any consumption. Each agent is enabled to perform the task over 500 episodes in the same Gridworld. After reaching one of the 4 objects, the agent gets a numerical reward chosen from the Dirichlet distribution with concentration parameter alpha 0.0.1. That means that there's only one object that has the highest value, while the other three objects that are called distractors have much smaller values. Besides, the agent is penalized 0.01 for each step, which is the movement cost, and 0.05 for walking into the obstacles. About the agents playing in the grid world, based on instance-free learning theory, we have developed an instance-free learning agent in the grid world. Briefly, instance-free learning theory provides a generic decision-making cognitive algorithm that can generate predictions of human behavior in various types of tasks. It also leverages cognitive mechanisms for memory, such as decay, recency, frequency biases, pattern matching through blending mechanism. Please refer to our paper for more details. So in the grid world task, an instance, that is a memory unit in instance-free learning theory, is defined by attribute, state, action, and outcome. The outcome is the expected utility resulting from taking action in the corresponding state. So when making a prediction about which action the agent will take at one state, the instance-free learning agent selects the action with the highest expected utility using the blended value. Importantly, as the agent only knows the consequence at the end of each episode, we adopt a delay feedback mechanism of instance-free learning theory to the grid world task. Here, we distribute a final outcome equally to all actions taken in a trajectory. We then compare the performance of the instance-free learning agent against two reinforcement learning agents called Q-learning and SARCSAR. They are both well-known temporal difference techniques in reinforcement learning. The basic difference between the two reinforcement learning algorithms is that SARCSAR is the on-policy method, while Q-learning is the off-policy learning method. We also built a random agent as a baseline for the comparison. In our experiment, we designed levels of complexity by manipulating cost-benefit trade-offs. In particular, the complexity is characterized by the difference, delta, between the distance from the agent to the highest value object, denoted by D, and the distance from the agent to the closest distractor, denoted by D prime. So as we can see, the high value of delta indicates the highest conflict between consuming the highest value object with greater distance D and consuming the distractor, a low reward object with a smaller distance D prime. In the first example, the distractor is the orange object and the highest value object is purple. So this case is considered a simple setting, as the distance to reach the highest value goal and to the distractor is nearly equal. By contrast, in the last example, we can see that the choice is more complex, since getting the highest value goal, the blue object, is more costly than consuming the distractor, the yellow object. So as a result, the agent is easily attracted to the closer but also lower reward object. About independent variables, we study 4 levels of complexity by varying distance from the agent to the distractor from 1 to 4. We examined 4 types of agents: Q-learning, SARCSAR, instance-free learning, and random. For each of the 4 levels of complexity, we generated 100 grid worlds for 100 agents of each type. We then evaluated the performance of the agent over 500 episodes. Regarding dependent variables, we considered 4 measures. First, fraction of object consumption, which is the proportion of episodes in which an agent reaches one of the 4 objects. Then we calculated fractions of steps, the average ratio between the number of steps for reaching one object and the maximum number of steps, which is 31 in our case. The next measure is accuracy, which is the proportion of episodes in which an agent successfully obtains the highest value object. And finally, efficiency is the normalized ratio between the reward for consuming an object and the movement cost. So here are the results that we observed. So in terms of consuming any of the four objects, we see that the fraction object consumption for Q-learning, SARSA, and instance-based learning is nearly equal to 1, regardless of complexity. Unsurprisingly, the random agent is the worst, but it gets better with the increased complexity. This is due to the environment design, that the more challenging the setting is, the closer the agent is to a destructor. So as a result, it's more likely to bump into an object. Regarding the fraction of steps, the instance-based learning agent took about same step to get an object as the complexity increases, while the Q-learning, SARSA, and the random agents took slightly less steps with the larger complexity. Again, the most likely explanation is due to the environment design. In terms of accuracy, the results show that in the simple decision settings, the accuracy of reinforcement learning agents and instance-based learning are comparable. However, when a decision complexity increases, the accuracy of instance-based learning agent drops slightly, while those of Q-learning and SARSA agents drop significantly. We also see that the performance of random agent does not depend on the complexity due to its random characteristics. With respect to efficiency, we observe that in a simple decision setting, the Q-learning and the SARSA are the most efficient agents. So the higher value of efficiency indicates that the reinforcement learning agents can obtain the highest value object within a limited number of steps. Conversely, when the setting becomes more complex, the results show that the instance-based learning agent is the most efficient. We also analyzed the average accuracy for each type agent over the course of 500 episodes. And we see that the instance-based learning agent learn slightly faster than the reinforcement learning agents, even in the lower levels of complexity. And in the more complex settings, the learning speed of the instance-based learning agent decreases, but the difference between the instance-based learning and the reinforcement learning agents is significant. So the random agents does not learn since its learning curve is nearly constant. We further run the Q-learning and the SARSA algorithms over 3,000 episodes under the highest level of complexity. And the results show that the two agents have a low start, but after 1,000 episodes, they continue to learn to be more accurate. So it can be explained that with one step update of state action values, the reinforcement learning models might not have gained enough experience to learn the correct value of objects within 500 attempts, while the instance-based learning model leverages all the past instances to update, resulting in faster learning. So to sum up, the experimental results revealed some interesting behavior of the agents with the increased complexity. And we see that in terms of accuracy and efficiency, even though in lower levels of complexity, the instance-based learning agent is less efficient than the reinforcement learning agents, under higher complexity levels, it turns out that the instance-based learning agent is more accurate and efficient. So that's all for my presentation. Thank you for your attention.